In this video, what I would like to show you is a way that you can convert from one quantity of a mole to another. And I'm going to be putting on the whiteboard up here a diagram, and I'm going to suggest you copy this into your notebook, make it big. And I'm going to show you how from moles to mass, volume, number of particles, all these things can be interrelated to one another. I'm going to start off by putting mole in the center of my diagram. Mole is going to be the hub to this map or to the conversion process. Up on the one corner, I'm going to put mass. You can put these in any position. I'm just going to keep with this pattern here. Over here, I'm going to put number of particles, and those particles could be, I'm going to list them here, atoms, molecules, or even ions. And you could count and you could measure a lot more things than just these, but these are the typical ones that we deal with when we're doing chemical conversions. So I got mole, mass. Over on this far side, I'm going to put volume. And then down to the right-hand corner, I'm going to put put energy. And I'm going to connect all these with a line. So it looks like the hub of a wheel, and these would be like spokes going out from the wheel or coming into the wheel hub. Now, the things that I have to use when I make conversions from one unit to another are some tools that you're familiar with. The periodic table is the tool that I use to go from mole to mass or from mass to mole. So I'm just going to put the initials PT up here to represent I have to use the periodic table. Down in this corner, the number that I have to use in order to get particles is the number that we've seen up on our board here, Avogadro's number, and I'll write it in the scientific method notation, 6.02 times 10 to the 23rd. And then to get to volume, this will have to deal with gaseous materials. Liquids it doesn't apply to, but you recall maybe seeing the 22.4 liter box. Well, that represents a mole of a gas at conditions of standard temperature and pressure, which I described in another video as being 0 degrees Celsius and 1 atmosphere of pressure. When you have gases at this condition, and that's pretty easy to achieve, a cold day, probably a nice day where the atmospheric pressure is not like stormy weather. And if that's the case, you might have to change this number down here. But if it's a nice day, cold outside, freezing cold, then the amount of gas that you could put into the container would take up this amount of space, 22.4 liters. If the temperature was warmer, in other words, if we were to change this to be like room conditions, 25 degrees Celsius, that's comfortable, then the box would have to get bigger. And instead of having 22.4 on the side of the box, I would have to put down in here 24.5 liters. So the gas would cause the box to expand a little bit. Well, this box was made for just this one type of demonstration, and we don't have a second box of this type that has the larger dimensions to it. So we'll just make the conversions as was needed. And let me go back to my diagram up here. In order to go from moles to volume, the number that I need, and this is for gas, not for liquids or solids, just for gases, The number that I need is 22.4 4 liters. And that's for conditions of that 0 degrees Celsius, 1 atmosphere of pressure. That's called standard temperature. Standard temperature and pressure. Standard temperature and pressure, and it's abbreviated by the letters STP. So if a chemist was talking about conditions of STP, another chemist would understand what that means. The other number I want to put up here is the one that's for the larger volume, 24.5 liters, and that would be for room conditions. So the temperature would be 25 degrees Celsius and 1 atmospheric pressure, 1 atm. Over here, for the standard temperature and pressure, it's 0 degrees Celsius and 1 atmospheric pressure, 1 atm. You will see these numbers described in your text. The other type of conversion I can do is with energy. We tend not to get to the stages where we're talking too much about energy, but there's a whole bunch of conversion units that we can put in to do energy conversions. So this is a nice diagram that enables me to go from one kind of a unit to another. And if you think about the idea of the donuts, okay, if I have a certain mass of donuts, I can convert it to a quantity of donuts, a dozen in some cases, or even a mole, if you had a mole of donuts. If you counted 6.02 times 10 to the 23rd donuts, you could convert those to a mole. For volume, they take up a certain amount of space. Every donut has a certain volume to it. It's not a gas. And then energy is the amount of calories that you might find in a donut, so you could convert for that unit also. Now, in my diagram, if I'm in the middle and I want to go to one of the outer units, as I go out, I will multiply. So every time I go outwards from the center of the diagram, I multiply. So on these little spokes that I'm doing, I'm putting those times sign in. That would take me to the outside unit. And I can imagine sometimes I might have to divide, and divide would mean I'm going back into the diagram. So you can remember it in one way, and then the other is just the opposite. So if you remember that going out from mole to another unit, you multiply, then you'll have what you need to remember. Just remember that the division occurs when you come backwards, when you go into the center, to the mole. If you want to make a conversion where you go from mass but want to get to volume, what you'll do is put down the mass of a given substance, go this way, divide, that gets you to mole, and then you'd use one of these numbers up here, 22.4, 24.5, and that would be multiplied, and that would take you to the volume. Now, I'm going to show you an example of a problem that would be like that. Let me turn off the video for a second here. I want to show you here a way that you can do a conversion of a substance. I'm going to talk about a gas. Let's suppose somebody has a party balloon and it's filled with helium gas. If we were to weigh the balloon and get a number for it, we could also take that value, and using our diagram for the mole conversions, we could go from mass through mole and get the volume that the balloon would take up in terms of space. So let me show you how I can set that up as a problem. I'm going to start with a quantity. Let's suppose the balloon has, when I weigh it, it has 6 grams of helium in it. Okay, I'll start with that. I'm going to do what we call factor label calculation, or dimensional analysis, where I put some unit on the top, another equivalent unit in here. I try to get parts of the sections of the problem to cancel out, making sure units cancel out, and eventually end up with an answer. So with our diagram, and I want to go from mass to mole, I'm going to go this way. I'm going to divide. So I have to go to my periodic table. That's the tool that I use for this calculation. And I have to divide, so I got to put a number on the bottom. So I look up helium on the periodic table. It has a mass of roughly 4 grams. That's what 1 mole would be. That gets me to the calculation where I will have the helium gas calculated as mole. And if I do that division on a calculator, just take a calculator and do 6 divided by 4, that'll give you a number. And then I can do my next step, which is to go from the mole quantity to my volume quantity. So going back over here, I'm going to pick one of the volumes that's in my diagram. Let's suppose it's a party balloon that it's at room conditions. So I'll consider the volume to be 24.5 liters, the little larger size box that we talked about. And my next calculation would then be to go out in the diagram. So I'll multiply. Here I divided. Now I'm going to multiply 24.5 liter helium, and that's equivalent to 1 mole of helium in volume. So there's the setup to my problem. And I have everything put in a factor label problem where I can use this process of dimensional analysis. I can cancel some units out, and then eventually I will get my answer. So let me take a different pen here and cancel out what I can see is similar. Up here I have grams of helium. Down here I have grams of helium. One's on top, one's on the bottom. I can cancel those out. I'm going to look for something else in my problem to see if I can cancel it. Up at the top I have moles of helium. Down here I have moles of helium. Let me cancel that out. I'm left with one unit, liters of helium. It doesn't cancel with anything, so I know that my answer, when I do the math, is going to have this as the final unit. So I'll put liters of helium, and then on a calculator, I'll take 6, I'll divide it by 4, whatever that answer is, I'll multiply it by 24.5, and that will become the answer that I want. And I did that just a moment ago when you weren't looking. And my answer is 36.75, and that'll be my liters of helium. Let me put that down. 36.75 liters. So doing a simple calculation like this, I can use all my units. I can make my conversions from the diagram. This map here tells me how I can set my problem up, and I'll try to show you some other examples of calculations using this diagram, but that'll be in another video.